Hello everyone, we continue our course of lectures, formal languages, automata and codes. And first of all, I recall you that all our lectures you can find in my website. It's here, lecture number 10. Also, this website you can find Ukrainian version of my language, my course. So this course contains a theory of codes and automata. So we shall start. Good. Today we have lecture number 10, and it will be devoted to non-negative matrices. So now we consider property of non-negative matrices. Let Q be a set of indices for two Q vectors V and W with real coordinates. One writes V is less or equal W if VQ is less or equal the WQ for Q from Q capital, and V is less of W if VQ is less the WQ for all Q from Q capital. A vector V is said to be non-negative if V is equal or greater 0, and V is said to be positive when V is greater 0. Here and below we denote by 0 the null vector or the null matrix of appropriate size. In the same way, for two Q times Q matrices M and N with real coefficients, we write as M is less or equal to N when MPQ is less or equal to NPQ for all PQ from Q capital, and M is less N when MPQ is less NPQ for all PQ from Q capital. The Q times Q matrix M is said to be non-negative if M is equal or greater 0, and said to be positive if M is greater 0. We shall use often the elementary fact that if M is greater 0 and V is equal or greater 0 with V non-equal 0, then M multiply V is greater 0. A complex matrix number lambda is called equivalent of matrix M if the matrix lambda multiply the unit matrix minus M is not invertible. In this case, there exist vectors V and W, V distinct from 0 vector, such that MV is equal lambda V and double VM is equal lambda double V. The vector V are left and the right equivectors corresponding to the equivalent lambda. So the vectors W and V are left and right equivector corresponding to the equivalent lambda. The spectral radius of the matrix is the maximal modulus of its equivalence. A non-negative matrix M capital is said to be stochastic if the sum of its element on each row is equal 1. Equivalently, the matrix M capital is stochastic if the vector V with all complements equal to 1 is a right equivector for the equivalent 1. Proposition. The spectral radius of stochastic matrix is equal 1. The proof. Let lambda be an equivalent of the n times m stochastic matrix M capital. Let V be a corresponding right equivector. Dividing all components of the vector V by the maximum of the modulus, we may assume that the modulus of coordinates of vector V Vj is less or equal 1 for all j from 1 to n, and the modulus of Vi is equal 1 for some I. Then we have that the product lambda Vi is a sum of such products from I from 1 to n implies that the modulus of lambda is less or equal of such sum, which is less or equal of such sum, which is equal 1. This completes the proof of the proposition 1.9.1. The adjacency matrix of the finite deterministic automaton A capital over the alphabet A with the set of states Q is a Q times Q matrix M capital with the coefficient MPQ, which is equal to cardinality of such letters from alphabet A, such that P multiply A is equal Q, which let K be the cardinality of the alphabet A. The matrix M divides K is stochastic. A corresponding right equivector is the vector with all components equal to 1. It is also an equivector of the matrix M capital for the equivalent K. By the proposition 1.9.1, the spectral radius of the matrix M capital divided K is equal to 1, and therefore the spectral radius of the matrix M capital is K. If the matrix M capital is a adjacency matrix of the graph G, a useful way to think about the equivector V of the matrix M capital is that it assigns a weight V Q to each vertex Q. The equality M capital multiply V is equal lambda multiply V correspond to the conditions that for each vertex P, if we add up to the weight of the end of all edges starting at P, the sum is lambda times the weight of the vertex P. A non-negative matrix M capital is said to be reducible if for all indexes PQ there exists an integer k such that MPQ in power k is greater than 0, where M in power k denotes the k power of M. Otherwise, the matrix M is called irreducible. It's easy to verify that the matrix M capital is irreducible if and only if the sum of unit matrix and matrix M capital in the power n is greater than 0, where n is a dimension of the matrix M capital. It is easy to prove that the matrix is reducible if there exists a reordering of the indices such that the matrix M capital is blocked triangle. So this is well known from linear algebra. That is the form of such form here, with the matrix U and M of dimension greater than 0. The following result is the part of the theorem which is known as Perron-Frobenius theorem. It says in particular that the spectral radius of the non-negative matrix is an value. Theorem, the Perron-Frobenius theorem. Any non-negative matrix M capital has a real equivalent rho M such that the modulus of lambda is less or equal to rho M for any equivalent lambda of the matrix M, and that corresponds to rho M a non-negative equivector V. If the matrix M is irreducible, then there corresponds to rho M is a positive equivector V. We observe that the same result holds both for right and for left equivectors. Before the proof, we state a result of independent interest which will be used in the proof. A sequence of matrix Mn, where M belongs to the non-negative integer of real M times M matrices, is said to be converse if the setting Mn APQ in the power n, each of the real sequences that converges. A series of matrix Mn converges if the sequence Sm defined by this sum converges. Proposition: let M be an M times M matrix with real coefficients if the spectral radius rho of the matrix M satisfies the condition that rho is less 1 than the sum of matrix Mn converges. Proof: we put nz is equal the unit matrix minus the matrix M multiplies that, where I is the identity matrix and Z is a variable. The polynomial nz can be considered both as a polynomial with coefficients of the ring of M times M matrices, or as an M times M matrix with the coefficients in the ring of real polynomials in the variable Z. The polynomial nz is invertible in both structures, and its inverse can be turned to view it as a power series of with coefficients in the rings of M times M matrices, or as a matrix whose coefficients are a rational fraction in the variable Z. The radius of convergence of the inverse polynomial viewed as a power series in Z, which with the matrix coefficients is equal to the minimum of the radius of convergence of the element of nz in power minus 1, viewed as a matrix of power series expansions of rational fraction. All these rational fractions have a denominator determinator I minus mz. Thus, this radius of convergence of the expansion of each rational fraction is at least one device row. Consequently, the radius on convergence nz in power 1 is at least one device row. This completes the proof of our proposition. Next, we shall prove the Frobenius theorem. Let us first show that one may reduce to the case when the matrix M is irreducible. Indeed, if the matrix M is reducible, we may consider a triangle decomposition as in equation 1. Apply by induction the theorem to U and V, we obtain non-negative equivectors U and V for the equivalent row U and row V of the matrix U capital and V capital. We prove that maximum of these equivalents is an equivalent of the matrix M capital with some non-negative equivectors. If rho U is greater or equal rho V, then rho U is an equivalent of the matrix M capital with the corresponding equivector U0. Yeah. If rho U is less of rho V, then we show that rho V is equivalent of the matrix M capital for the equivector U prime V, where U prime is the following product. So let's assume it is equal the product of inverse of U minus I minus U divided rho V multiplied to V. Since rho U is less rho V, the such series converges by proposition 1.9.3, and it converges to a matrix with non-negative coefficients because each power Vn has a non-negative coefficients. It follows that U prime has non-negative coefficients. Moreover, we have V capital multiply V is equal rho V multiply V rho V here, and is equal rho V multiply U prime minus U capital U prime, showing that this product is equal the following product. This shows that rho M is greater or equal a maximum of rho U rho V. Consequently, if lambda is equivalent of the matrix M with a corresponding equivector UV, then lambda is the equivalent of matrix W if V is not equal 0 and lambda V is not 0 vector equalist, yeah, and lambda is the equivalent of the matrix U capital if V is a 0 vector. This proves that rho M is equal to maximum of rho U and rho V. Next, we suppose now that the matrix M capital is irreducible. For any non-negative Q vector with distance from 0, we put rho M of V is the minimum of such M VI divided VI. Therefore, rho M of V is the largest real number R, so that MV is equal or greatest rho V. One has rho M on lambda V is equal to rho M on V for any real numbers lambda distant from 0. Moreover, the mapping which posits V rho M of V is continuous on the set of non-negative non-zero vectors. The set X is of non-negative vectors V such that model V is equal 1 is compact. Define rho m by rho m is a maximum of such rho m W, where W belongs to the set X capital. Since the continuous function of the on a compact set reaches its maximum on this set, there exists an element X from X capital such that rho m of X is equal rho m capital. Since rho m of V is equal to rho m of lambda V for lambda distinct from 0, we have that rho m is equal maximum of rho m W, where W is positive and distinct from 0. We show that mx is equal rho m of x. By the definition of the function rho m, we have that mx is greater or equal to rho m of x. We put y is equal mx minus rho m of multiply x. Then we have that y is greater or equal to 0. Assume that m of x is not equal to rho m of x. Then y is not equal to 0, since I plus m is a power m, where I is identity matrix, is greater than 0. This implies that the vector I plus m in power n multiply y is positive, but we have that I plus m in power n y is equal I plus m in power n multiply m x minus rho m of x is equal to m multiply y capital plus m in power n multiply x minus rho m multiply I plus m in the power n multiply x. And this is equal to m z minus rho m of z, where the z is equal to such product I plus m in power n multiply x. This shows that mx is greater than rho m of x, which implies that rho m of z is greatest rho m. As this contradicts with the definition, of the notion rho m. This shows that rho m is equivalent with a non-negative equivector, and let us show that rho m is greater or equal modulus of lambda for each real or complex equivalue lambda of the matrix M capital. Indeed, let V be an equivector corresponding to lambda, then μv is equal lambda multiply V. Let modulus of V be a non-negative vector with the coordinates modulus Vi, then m multiply modulus V is greater or equal modulus of lambda multiply modulus of V by the triangular equality. By the definition of the function rho m, this implies that rho m of modulus of V is greater or equal modulus of lambda, and consequently we get that rho m is greater or equal modulus of lambda. We have already seen that the corresponds to rho m a non-negative equivector x. Let us now verify that x is greater than 0. But this is easy because I plus m in power n multiply x is equal 1 plus rho m in power n multiply x, which implies that 1 plus rho m in power n multiply x is greater than 0. And hence we get that x is greater than 0. This completes the proof of the parent Frobenius theorem. Example, we consider the matrix M such the equivalent of matrix M are phi is 1 plus square of 5 divided 2, and phi 1 minus square of 5 divided 2. It the roots equation z square minus z minus 1 is equal 0. Z corresponds to phi, the non-negative left equivector phi 1. An example of application of the parent-for-parent theorem, we obtain the following result. Proposition 1.9.5. Each stochastic matrix has a non-negative left equivector for the equivalue 1. The proof. Let M be a stochastic metric. By proposition 1.9.1, its spectral radius is equal to 1. The theorem the theorem of Perron-Frobenius implies by this theorem there exist corresponding non-negative left equivectors. Recall that the adjacency matrix of the deterministic automaton, our K letter alphabet, has radius of convergence K and has a corresponding right equivector with all components equal to 1. By theorem 1.9.2, it has also a left equivector with a non-negative component corresponding to the equivalue Q. Let K be an integer. K approximate equivector of a non-negative matrix A capital is by definition a vector V distinct from zero vector with the integer non-negative components such that M capital V is less or equal KV. Again, if one assumes that the matrix M capital is a adjacency metric of the graph G, then an approximate equivector of the matrix M capital assigns to a non-negative integer which VQ for each vertex Q. And the vector equality M capital multiply V is less or equal K V corresponds to the condition that for each vertex P, the sum of the weight of the ends of all edges starting at P is at most k times of the weight of P. We shall use the following result. Proposition 1.9.6. And irreducible non-negative and integral matrix M capital with spectral radius lambda admits a positive K approximate equivector if and only if K is greater or equal to lambda. The proof. Suppose first that K is great of lambda. Consider the matrix N, which is equal the product K multiplied the additive matrix I capital minus M. Since K is greater lambda, we have that determinant of matrix M is greater of 0, and therefore the matrix N is invertible. Moreover, since the inverse matrix of N is equal such, and since M is irreducible, the matrix inverse to M is positive. Let V be a column of the matrix N power minus 1 or inverse to matrix. And we have that N multiply V is greater or equal to 0, and hence we get the M capital multiply V is less or equal to KV. Any columns of the inverse matrix of N is then a positive K approximate equivector of the matrix M capital. If K is equal lambda, by theorem 1.9.2 there exists a positive vector V such that MV is equal KV. Since lambda is an integer, the coefficients of the vector b can be chosen to be integer. Let us finally prove that consequently, if the matrix M capital admits a positive k approximate equivector v, then k is greater or equal lambda. Consider the matrix M with the product is in such a matrix M on the value inverse to lambda by the Peron theorem. There exists a positive vector W such that n capital multiplied W is equal W. We have that n capital multiplied V is less or equal k divides lambda multiply V. This implies that n capital in power n multiply V is less or equal k divides lambda multiply n in power sorry, it's correct, it must be k. This is incorrect, this must be in the power n multiply v for all positive integer n. Good. If lambda is greater than k, then the right hand side tends to 0 as n tends to infinity, and therefore we get that n in power n tends to the 0 matrix, which contradicts with the fact that the n in power n multiply v w is equal w, or with v greatest 0 vectors. This completes the proof of the proposition. An example, we consider such matrix M. The spectral radius of the matrix M capital is strictly less than 2, and two approximate equivectors is such 1, 1. So we finish our lecture. I wish you good luck and good health. Goodbye.